When tracking the pathology of Alzheimer's disease, the first nucleus to exhibit tau accumulation is the locus coeruleus. Throughout all waking hours, this small brainstem structure fires tonically. This continuous activity creates a metabolic ceiling. Autonomous pacemaking, combined with the autooxidation of its own catecholinergic transmitter, subjects the nucleus to a relentless calcium and oxidative load. Traditional bioenergetic models describe this metabolic demand as an unceasing 24-hour cycle of damage and repair. But that model ignores the behavioral and electrophysiological state of the organism. A biological system does not operate at peak metabolic load continuously. The locus coeruleus degrades because, over time, its daily metabolic expenditure outpaces its available recovery window. This graph maps the locus coeruleus firing rate across a daily cycle: high tonic firing during waking, tapering downward during non-REM, and flatlining in REM sleep. Sleep is the only phase where the nucleus is entirely silent, halting its pacemaking activity. This electrical silence provides the necessary temporal phase for the cell to run mitochondrial quality control and clear its accumulated oxidative debt without adding new metabolic strain. Because the locus coeruleus is the primary source of noradrenaline for the cortex, its firing state dictates the chemical environment of the entire brain. When the nucleus falls silent, the resulting system-wide withdrawal of noradrenaline changes the biochemical state of the entire central nervous system. The effects of this silence extend past the internal recovery of a single nucleus. The nightly drop in noradrenaline acts as the permissive neurochemical signal that initiates a pan-axis restorative state. We can visualize this timing mechanism as a continuous 24-hour oscillator. This wave represents the diurnal concentration of noradrenaline, cycling between high peaks and deep troughs. During the waking state, the peak of this wave, the brain is flooded with norepinephrine. This high concentration binds directly to beta-2 adrenergic receptors on microglia, actively suppressing their process motility. The cells remain rigidly in place. Throughout the day, this suppression acts as a necessary brake, restraining the microglia from triggering reactive inflammation in response to normal daytime cellular stress. As the brain enters sleep, the norepinephrine wave tracks downward into its deep trough. In this low norepinephrine environment, those microglial receptors unbind. The brake is removed. The microglial cell extends branching processes, entering an active surveillance and inflammatory reset phase, scanning the local neural tissue for damage. Norepinephrine operates with a double edge. High daytime concentrations restrain reactivity, while low nighttime concentrations permit essential surveillance. A functioning neuroimmune system that depends entirely on this alternating, predictable diurnal rhythm. Sleep is the scheduled maintenance phase for the brain's resident immune cells, and that schedule is strictly dictated by the pacing of the locus coeruleus. This same chemical timing governs the physical wiring of the brain, a process described by the synaptic homeostasis hypothesis. The core premise is that waking experience drives a net potentiation. Throughout the day, learning and attention cause synapses across the cortex to physically grow and strengthen. By the end of the day, this accrued structural growth becomes metabolically demanding and consumes finite physical space, making it biologically unsustainable. Slow-wave sleep serves as the specific physiological mechanism to proportionally scale down the size and strength of these synapses. This structural downscaling is directly connected to the neurochemical environment. High noradrenaline promotes growth. Low noradrenaline from the sleeping locus coeruleus permits synaptic pruning. The fast-spiking parvalbumin interneuron fires at high frequencies, making it the most metabolically demanding neuron in the cortical circuit. To survive its own extreme workload, this specific interneuron requires the surrounding excitatory synapses to be scaled down every night. If sleep is lost, that downscaling never occurs. The excitatory drive remains high, and the interneuron is forced past its oxidative buffering tolerance. The physical architecture of the cortical circuit relies entirely on the locus coeruleus reliably shutting down every night to allow for this renormalization. The primary neurochemical actuator opposing this necessary rest is orexin. Produced in the lateral hypothalamus, Orexin stabilizes wakefulness by supplying a continuous, tonic excitatory drive directly to the locus coeruleus. In early Alzheimer's disease, accumulating tau pathology causes sleep fragmentation and hyperarousal. This creates a massive endogenous noxious load. The sustained excitatory drive forces the locus coeruleus to continue firing straight through what should be its nightly recovery window. The result is a self-amplifying positive feedback loop called the restorative interval spiral. Early pathology fragments sleep. This fragmentation withdraws necessary repair mechanisms across all axes, accelerating damage to the locus coeruleus, which degrades sleep further. Returning to the 24-hour oscillator, the healthy noradrenaline wave cycles between high peaks and deep troughs. As advancing tau kills locus coeruleus neurons, the wave's amplitude collapses. Reaching a critical tipping point, the oscillation flattens completely into a horizontal line, leaving chronically low noradrenergic tone. Losing the high daytime peak permanently removes the necessary braking mechanism on microglia. Without that restraint, reactive inflammation is disinhibited. Simultaneously, losing the deep nighttime trough abolishes the scheduled release required for microglial surveillance and synaptic downscaling. The destruction of the locus coeruleus degrades the temporal architecture required to keep the brain's restorative programs functional. When evaluating the clinical literature on sleep and Alzheimer's disease, we encounter a strict epistemological limit. Human sleep data is overwhelmingly cross-sectional. This situation creates a reverse causation paradox. The data clearly shows a correlation, but it cannot definitively answer whether poor sleep causes Alzheimer's or whether early brain damage causes poor sleep. Under the restorative interval framework, the exact direction of causation does not invalidate the physiological mechanism of failure. Whether the sleep cycle is fragmented by external stressors or by the disease's intrinsic damage to the brainstem, the outcome is identical, a withdrawn restorative state. This defines a strict therapeutic window for phase-resolved interventions, such as orexin antagonists to block the wake drive, or acoustic stimulation to enhance slow waves. These treatments must occur while the locus coeruleus still possesses enough structural integrity to receive the rest it was built for.